Dr. Hicks is the lead software developer at Quantum Benchmark Incorporated. His research interests are in the development and implementation of scalable methods for characterization, control, and tune-up of noisy quantum processors, with an emphasis on gate randomization. Ian obtained his PhD in experimental quantum characterization and control from IQC at the University of Waterloo, Canada, working with nitrogen vacancy centers in Diamond. So it's a pleasure to have Ian with us today. And I pass the proverbial floor to you to share your slides and begin your presentation, please.
Thanks very much, and thanks for having me. It's nice to be here. So I'll just share my screen. To choose the right window. Okay. So that's working, and you can see my cursor, I think.
Looks good.
Okay, great. So the title of this talk is Scaling Up Quantum Processors, Diagnosing Errors and the Unknown Unknowns. So I wasn't really sure of the background of everybody at this talk. So I have a bit of everything. I have some experiment, I have some theory, and so hopefully there's a little bit of something for everyone. If there's one thing that I'd like you to take away from this is that I believe that if you think that keeping track of errors is important on noisy quantum devices, then you should really be thinking about the primitives of that device as being cycles. And I'll define exactly what I mean by cycles in a bit. But just roughly, a cycle is a collection of instructions that you send the quantum processor that happen in a contiguous block of time in a fixed order that happens every time you do that particular collection of things. So usually it's a set of simultaneous CNOT gates or something like that, or a simultaneous set of single qubit gates, something along those lines. And then next, I need to introduce a little bit of background. So I'll introduce something called the Pauli transfer matrix and cycle twirling. And after that, I'll talk about a very important application of cycle twirling called randomized compiling, which is a way to improve the performance of an application quantum circuit. And then I'll talk about how do we actually characterize the errors of these cycles, and maybe a little bit of how we might fix up problems with cycles at the gate level. And finally, I'll show a way that we think that we can scalably quantify circuit performance. So I'll dive right in. So at the end of the day, what we have on a quantum device is, if it's a gate-based device, our interest is in feeding in an input state to some application circuit. You choose your favorite application, it could be anything, and we sample bit strings from the output. Now, this is what I mean by a cycle. I'd like you to picture this circuit as being divided up into a sequence of collections of gates. And these are going to be our primitive instructions that we'll talk about the errors of. So I'm going to start with some motivation for why I'd like you to think about the primitive operations of quantum devices being cycles of gates rather than just the gates themselves. And so I'll start with some data. So if you look at IBM Q's set of quantum devices, they have a number, some are private, some are public. Here's a list of 5 of the public ones, which all have the same topology. So each dot in this graph is a qubit, and there are you can apply entangling instructions between any of the connected points on the graph. So here are 5 of them: Burlington, Essex, London, Urance, and Vigo. So what we did is we isolated 4 different cycles on these 5 devices which share the same topology. So in the first cycle, you idle 3 of the qubits and you apply a CNOT on 2 of the qubits. And in the second, you do the same thing. You idle on 3 of them, but you apply a CNOT on another pair of qubits, and so on. And so what we can do, and I'll talk more about how this is done in a little bit, but what we can do is for each of these 4 cycles and for each of these 5 devices, we can measure the quality of this cycle. Technically, we're measuring the process infidelity, which I'll define later. But all you need to know right now is that a low value is good. And so what I've done is I've measured them in two different ways. In the top one, I've included the error of the C naught, but also the induced error of the idling qubits on the other three qubits. And I've sorted them, so from best to worst. So this blue dot on the left is the best cycle out of all the chips, out of all the 4 possible cycles, and it goes all the way up to the worst one, which is quite bad. And now on the bottom, I'm sorting them in a different way. Instead of including all the qubits in the device, so including the noise that's induced on the idling qubits and not just the qubits that are involved in the CNOT gate himself. So just restricting to the CNOT qubits, we can also sort. And you'll notice that the scales are different on the plot, because when you restrict to just the CNOT, the gates get quite a bit better because you don't have any errors on the other 3 qubits. And what you'll notice is we're drawing a line between cycles. And so you see a lot of diagonals in the lines, which means that the ordering is completely different. So a cycle which is quite good when you just restrict to the 2 qubits of the entangling gate can actually be quite bad if you include the effects that are happening on the other 3 qubits. And on the right, I've sort of shown the correlation between these 2 metrics. So I think on the y-axis is the bottom set of points, and on the x-axis the top set of points, and we're plotting them against each other. And so they sort of look weakly correlated. And keep in mind that there's an upper bound, a diagonal upper bound here. So the blue points have to be below that point. So the correlation is actually a little bit weaker than it even looks.
Can I ask a question?
Yeah.
What are the error bars for all those dots? Because they are not infinitely known exactly, right? So the order on your left plot also includes some statistical variation.
Yeah, sorry, this is a very new plot, so I didn't put error bars on, but I'm going to show a plot around the middle of the talk where I show the exact same points in a different format, but with error bars. But just for your eye, if you can see my cursors, they're from about, oops, sorry, they're from about here to here. They vary. Some of them are big, some of them are small. But I trust this ordering basically. To some degree. Thanks for the question. So now we'll get into some preliminaries, unless there are any other questions about this plot, which I'm happy to answer. So I get the takeaway from this is that you shouldn't really, if IBM reports or anybody reports just the C0 fidelity, it's not a great indication of how well that C0 will perform in a circuit, because of course in a circuit, the other qubits will be involved later in the circuit, and errors induced on them during that C0 are relevant. So we'll go through a little bit of preliminaries so I can talk about exactly what we mean by error and how we measure it. So of course we describe quantum states as density matrices. So this is the state of the system at some point in time. And what you can do is you can write it out in terms of the Pauli basis. So Pn here is the Kronecker product of all possible Paulis. And what we can do is we can take these coefficients of the Paulis and we can put them into a huge vector. So this vector has length 4 to the n. And this is the vectorized density matrix in the Pauli basis. Now, any quantum channel and any physical mechanism that alters the quantum state is a linear map, and here I've called it lambda. And so if we see what it does to this vector, well, we get a process matrix. So it's a matrix which takes an input set of coefficients in the Pauli base and gives you an output set of coefficients in the Pauli base. And we call this matrix the Pauli transfer matrix of this quantum process. And so it's 4 to the n by 4 to the n, so it's huge. And so I can talk a little bit about the properties of this matrix. So you should think about it as having 4 blocks. So first of all, there's the top left. So this is just for a qubit, by the way. So it's 4 by 4 because there's only 1 qubit. But in general, the top left block is trace preservation. So usually this number is 1. And if it's less than 1, then it's a trace decreasing channel. So you're losing your state to some third level maybe. And this orange one at the top is state dependent leakage. So this is changing the trace of your density matrix as a function of what the state is. And then we have a non-unital piece. And an example of this is a T1 process. So you'll be, even if you put in a completely mixed state, you'll be going in some direction like Z because of thermalization. And then down here, which is what I'm really interested in this talk, is the unital block. And these are all the coherent dynamics and other and all the other dynamics. And the diagonal is representing state preservation. So for example, this lambda XX term is saying, well, how well does this map preserve the X thing? So if lambda XX is a 1, it means that it preserves the X completely. And if it's 0, then it's taking X to something else. And just as some examples, so on a single qubit again, if we have a rotation by theta about the y-axis of a single qubit, this is what the Pauli transfer matrix looks like. So of course, y is fixed because you're rotating about y, but x turns into z and z turns into x. And another example is a dephasing channel. So we're shrinking your state along the z-axis, but you're keeping the other 3 Paulis fixed. And so what we can do is we can take this Pauli transfer matrix and we can take the trace of it. And this is a quantity called the process fidelity. And it's a measure of how far away the channel is from the identity channel, the channel that does nothing. So we take the average of the diagonal, and then we can take 1 minus that. And so if you want your channel to be really close to identity, then you want E underscore F to be close to 0. And this is a really popular method of computing the error of a channel, partly because it's experimentally tractable to measure this in many situations, and also because it's easy to compute. So there are a number of reasons why people like this process infidelity. And operationally, you can kind of think about it as the probability of an error on average. So here's a little slice of experimental data again. What I'm doing is I'm plotting elements of the Pauli transfer matrix that were measured for some noise process for a smattering of diagonal elements. So on the x-axis is which diagonal element, and on the y-axis is what its value is. And the mean value is an estimate of E underscore F. So the mean value is an estimate of the process fidelity. And there's actually a nice bound. So these points can't have too much variance. You can prove that for any completely positive trace preserving map, if you know what that is. It's less than 2 times the process fidelity. So these could only go up to about here, which is nice to know. So now let's get back to cycles. So let's say that we have some cycle we want to perform, and we're going to call it G. And of course, when we actually run it on our device, it's not perfect, it's noisy. And we're going to call a noisy implementation of G theta of G. And so you can think about this thing in the blue box as the Pauli transfer matrix of the implementation of G. And what we can do is we can arbitrarily say, all right, well, let's pretend that theta of G is the ideal implementation of G times some error channel of G. And of course, errors actually happen while the gate is being performed, right? Quantum mechanics is time dependent. It's not like in reality, you actually have a perfect implementation of G, and then 0 seconds later, you have the error channel being applied instantaneously. But you can always do this fiction where you multiply theta of G by the perfect implementation, G dagger times G, and then you incorporate phi into theta and define this capital epsilon as the error channel. So ideally, what we'd like this epsilon G Pauli transfer matrix to be is the identity, because we want 0 error. So now I'm going to get into twirling. If I just go back a bit. So this epsilon G, right, is this Pauli transfer matrix, which is 4 to the n by 4 to the n. It's huge. And what we can do is we can make it slightly more tractable by doing a process called twirling. So what we can do is we can pick a finite set of unitaries called T. So T is just a set of operations, perfect operations. And we can define a new quantum process, which is e.g. averaged by conjugations of those things. So I'll give some examples in a sec, but so what I mean by this expectation is you take everything in the set of unitaries that you've defined, you left multiply by t and you right multiply by the inverse of t, and then you average over all of them. But usually in practice for experiments, instead of looping over all of them, because there might be exponentially many of them, you rely on the central limit theorem to tell you that many of your estimators are going to get good if you just use a finite sample of random elements of t. So one twirling group that became very popular around 2006 with the advent of something called randomized benchmarking was to twirl by all of the unitaries or equivalently by something called the Clifford group. The Clifford group is a set of unitaries which has a number of nice symmetry properties. But what happens is that we take this PTM that's dense and we reduce it to its diagonal. But not only that, we make all the diagonal elements equal except for the first element. And so these elements are actually equal to the average of these elements over here. You see some of them are 0.916 and some are 0.917. That's just numerical accuracy. It's not, they should all actually all be equal. And so we call this average channel epsilon with an overline to indicate that it's being averaged. And so now you've reduced 4 to the n parameters by 4 to the n parameters to 1 parameter. And what you'll notice is that the process fidelity of these two channels is the same because the average of the diagonal is the same. And that's the definition of process fidelity. Another choice of twirling is you can take like implementing, I'll go back for a sec, implementing, arbitrary specified unitaries on n qubits is really hard and requires a depth that's something like n squared. So they would actually be very bad gates when implemented. And same with Cliffords. It also takes a lot of gates to make a global Clifford. So what you can do instead is you can do something like, instead of using the global set of Cliffords, you can just use qubit Cliffords. And so every qubit just gets a random Clifford, a random single qubit Clifford. There are 24 Cliffords for a single qubit. And when you twirl, instead of getting a single element on the diagonal, you get exactly 3 elements. You get the average of these 3 blue ones, which are of the form identity and then some Pauli. And then you get one, which is the average of these 3 ones. Let me find them, xi, yi, and zi, and you get these red ones. And then you get the 9 other ones. And so you've reduced down from 4 to the n by 4 to the n parameters down to 2 to the n parameters. So in general, this scales as all possible combinations of p's and i's in a length n string. So this is a slightly weaker twirl than the one before because you get more parameters on the diagonal. And now we can introduce an even weaker twirl, which is the one that I'll be focusing on in this talk, where you twirl by all single qubit Paulis. And so this again diagonalizes the matrix, but it preserves the diagonals exactly. So all of the diagonal elements are equal to each other. And again, the process fidelity of epsilon is the same as the process fidelity of epsilon bar. Now, the diagonal element of an error matrix is basically telling you how well that error matrix preserves a given Pauli. So for example, if your initial state is plus along the x basis, then it's telling you that you're going to shrink in that direction by px. We can introduce a reciprocal convention where instead of describing it as a Pauli transfer matrix, we describe it as a convex combination of Pauli errors, or as a Pauli Krauss map. Lots of ways of talking about this. But basically, you take an input state, And the output state is a sum of probabilities of applications of polys. And so this looks a little bit different. Instead of shrinking x, x gets affected by q, but then it also gets affected by yxy, which is minus x, and zxz. And the reciprocal relationship between this vector p up here at the top and this vector q in the second line is given by something called the Walsh-Hadamard transform. It's very similar. If you've ever seen the Walsh basis of discrete functions, it's similar to that. And so and W is almost unitary. It's off by a scalar, so it's an orthogonal matrix. So this transformation is quite easy. But sometimes it's nice to look at this one above, and sometimes it's nice to look at this one. So now I've gone over some preliminaries, and I'll talk a little bit about why we want to twirl. So as I mentioned before, it introduces fewer parameters, 1 or 2 to the n or 4 to the n versus 4 to the 2n. And of course, 4 to the n, is it really that much better than 4 to the 2n? Maybe. But really importantly, it has a lower worst case error, which I'll show you in one sec. And the errors are more predictable, which I'll also get into. And what I really want to talk about is that if we twirl the errors in an application circuit, they're going to match the numbers that we measure in standard benchmarking protocols, which is really nice because it's really nice to have the errors in an application circuit match the errors that you measure experimentally in a one-to-one way. And we can also do something like bound the errors on a circuit performance experimentally, so we don't need to make assumptions about the model at all. So the first point that I want to talk about is just one slide on the lower worst case error. So what I've done here is I've taken a bunch of random error channels, a bunch of random error processes. They're selected from some distribution that's not important. They're pretty close to the identity operation. And on the x-axis, I've plotted the worst case error. And on the y-axis, I've plotted the worst case error after Pauli twirling. And by worst case error, I'm using something called the diamond norm, which is a standard method of finding the worst case error of a quantum channel. And what you'll see is that the worst case error always gets better. Everything's below the diagonal. And in particular, the worst case error corresponds pretty heavily to how unitary your error is. So if you have a lot of coherent error because your error is dominated by something like classical crosstalk or other kinds of control errors, then you are going to be down here in these yellow spots, or maybe somewhere in the middle. But the point is, you should probably expect some kind of advantage to twirling. So how do we twirl in practice? Well, there's a protocol called Randomized Compiling, which was introduced, I guess, almost 5 years ago by Joel and Joe, the founders of my company. The process is you take an application circuit, it's up here on the top left, and you divide it into cycles of alternating types. You alternate easy cycles, and by easy, I mean cycles which only have single qubit instructions. And they're called easy because historically their qualities have been better than entangling instructions like this CZ in this cartoon. So you alternate easy and hard cycles of your application circuit. And then what you do is you choose a bunch of random polys and you throw them everywhere in your circuit. However, you correct. So every time you put a random poly that's blue over here, you put one over here which counteracts it. So you have to propagate this poly through the CZ gate, and then you put the inverse twirl over here. And so this circuit in B actually has exactly the same unitary as your application circuit, but it has different gates all over the place. It's polytwirled. And the reason polytwirling is possible is because you can choose your hard cycles to be Clifford gates, which commute polys by definition. And you can choose your single gates to contain anything. For example, T gates, which makes this kind of randomized compiling universal. It's possible in universal computation. And then you don't really want to triple your gate count in your circuit. So you compile all your single qubits together. And so what you actually implement is the product of these three gates. instead of implementing all three of them sequentially on your device in time. So this is the process of randomized compiling. In the interest of time, because I want to show off some figures below, I'm probably going to skip over a bunch of theory for how and why randomized compiling works. And I'll skip to this slide. So right here, what I've done is I've taken my hard cycle, and I've conjugated it by my twirl, and I'm averaging over all possible twirls on my hard cycle. And what I get out is some new effective hard cycle. And I can write this hard cycle as the perfect implementation of the hard cycle, which you remember is represented by phi, and the perfect implementation of my easy cycle times some error matrix, right? And the nice thing is that this error matrix is polytwirled, which means that it's diagonal in the Pauli basis. And so I get these nice properties, and I'm able to measure this as in ways that I'm about to describe. So let's take a little look at how RC might look on some circuits. So here in this slide is simulation. So in this simulation, we're interested in quantum volume-like circuits. This is a type of circuit introduced by IBM. And what it is so first you have rounds of arbitrary 2-qubit gates, which apply all throughout your device. These are these random SU4s. And then you alternate that with qubit permutations. So pi is an n-qubit permutation. So these kinds of circuits are kind of hard to run on devices because at least superconducting devices have a fixed topology. And so, performing a random SU4 between two distant qubits in the topology is often annoying. So they use this as part of their device benchmarking. And so what we're going to do is we're going to apply randomized compiling to random quantum volume circuits. And you might expect not to get a gain in this case because the circuit's already random. But you actually do in fact get a gain. So what's plotted here, and again, this is a simulation, is on the x-axis, we plot the single qubit gate infidelity. I think this is a simulation on 4 qubits. And on the y-axis, we plot the 2-qubit gate infidelity. And on the color, we plot how much better the circuit is with randomized compiling. So 5 means 5 times better. And the metric we're using to quantify this is total variational distance. So basically the probability that the device reports the correct output bit string. And so things get better in both directions. So if you improve your single qubit gates, you're twirling more effectively, so things get better. If you improve your 2-qubit gates, then things also get better. But in particular, along these diagonals where your device is just getting better as a whole, you're reaching, this nice regime up here where you're getting a 5 times improvement. And this plot on the right is just a slice out of here. And then here's some experimental data. So this was actually taken by Irfam's group, in particular by Ravi and Eckel. And so they didn't use quantum volume-like circuits. They're pretty close. In this particular plot, they chose random circuits on a oh, shoot, I should have remembered this. I don't remember how many qubits this is. I think it might be 4. Is that right, Eckel?
Yeah, it's 4.
Okay, 4 qubits. So we're plotting the same quantity on the y-axis, so total variational distance, so probability that the circuit is outputting a correct bit string. And the orange is showing So each dot is a particular instance of a random circuit. And then we randomly compile that again. And so in the bare case, the total variational distance is larger on average. And you might be asking, what is the main mechanism for this improvement? And it's because you're improving the worst case error. So each of your cycles is getting a little bit better. And things propagate more smoothly through the circuit. So, so now I want to get into, well, how do we characterize the errors of cycles in a device? So up at the top here, I'm sorry, I skipped a bunch of the theory slides, so this equation might not be familiar to you. But what this represents is a randomly compiled circuit, right? So we've taken a fixed circuit, and each one of these thetas is a different cycle in the circuit that we've twirled over. So you can imagine that each one is a different cycle, and so we have a whole circuit here, but it's averaged over many, about 30 different random twirling operations. And so what we want to do is we want to take some particular cycle from the circuit, and we want to benchmark it. So what we can do is we can just take one of them, and in a new experiment, we can repeat it back to back and average over twirling operations. And we get a circuit that looks like this. So just the same cycle over and over. And what this really looks like is it looks like the diagonal error matrix of this particular cycle times its ideal implementation. So we get, M errors and M ideal implementations. And then we can commute everything to one side of this circuit, and we get some Pauli matrix to the mth power. And so what the cycle benchmarking protocol does is for various values of M, so various values of circuit depth, it measures some of these diagonal elements. And if you fit that exponential decay, so each one of these diagonal elements is getting its own unique exponential decay. If you fit a bunch of them, like's done in here. So here is this is again data from an IBM Q device. So we've taken a bunch of random elements from that diagonal, and we've decided that we want to experimentally measure them. So on the x-axis, we've chosen 3 different values of M, and we've measured the fidelity of that particular Pauli. And then we've put an exponential curve through each of them. And this is, the decay rate of this is giving an estimate of that particular element of the Pauli transfer matrix. And then if we take their expectation value, we know that that's equal to the process fidelity, so the quality of the cycle as a whole. And so there's a question on the second slide about what the error bars on the process infidelity was. So here are the process infidelities from that plot, where they're organized a little bit differently. So again, we have 5 IBM Q devices, and we have 6 possible different cycles on them. Because of the topology, we can actually enumerate all 6 possible cycles. Just waiting for that thing to go away. So we have 2 simultaneous C-naughts on these left 2 plots, and then single C-naughts on these right 4 columns. And then each color is a different chip. And so this plot quickly lets you see, which device is the best, right? So it's pretty clear from this plot that Vigo is the best across the board. It has the best cycles. And then the runner-up, is probably Essex or something like that. But it also gives you an idea of which cycle is good. So if you have some application circuit and you've decomposed it into cycles, where you can say, well, I have 3 of these cycles and 4 of these cycles and 2 of these cycles and 1 of these cycles. So you can get a very good idea of how well that circuit is going to perform, but only if you perform that circuit under randomized compiling, because only in that case do you get the one-to-one correspondence between the measurement that you made in your benchmarking protocol and the measure you're making on your twirled circuit, your twirled application circuit. so this is showing, we're taking all of these Pauli decays, all of these exponential decays from the diagonal elements of the Pauli transfer matrix. And we're just getting one number out. We're taking their average and reporting the process infidelity. We can actually get quite a bit more information because each of these decays, is telling you something about the noise process. And so in particular, let's say that you choose to measure the decay rate of this diagonal element, the one corresponding to x, y, z, x, y. That was just chosen at random. So first of all, by marginalizing your data, so basically taking the results from one qubit and ignoring the bit strings, from the rest of the qubit, or the bit values from the rest of the qubit, you can marginalize, and you can find out what the decay on just that one qubit is. This is a post-processing technique. So you've already taken the data, and now you're choosing to marginalize on just one qubit. You can also choose to take, different pairs of qubits and marginalize. And this is showing you, the rate of decay of x, y in the context of performing the cycle. And so you can take these different combinations. And so what happens is if you're interested in measuring, the marginalized decays of all of your qubits, you can actually do this in order 1 number of circuits, because the post-processing lets you isolate each one of these qubits in turn by averaging over your data. Also, if you want to reconstruct all 2-body marginals, well, that turns out to only take log n because you get a lot of compression in this post-processing trick. And so if you do this, and you apply the Walsh-Hadamard transform that I talked about before, which turns Pauli diagonals into Pauli error rates, you can make a big plot like this that I'll walk you through. So here I've chosen one of IBM's devices. This is the Urn's device. And along the top are 6 possible cycles that you can do on the chip. The color bar is telling you the magnitude of error. The y-axis is telling you which error. And the x-axis is telling you to which qubit. So for example, this red one that I've circled, it's the total Z error on qubit 3 in the context of applying a C0 to qubits 1 and 2. Right? And so every one of these squares can be interpreted like that. So here's another one over here. This is the probability of getting a Zi error on your CX gate on qubits 3 and 4 in the context of applying CXs to both qubits 0, 1 and qubits 3 and 4. And because I've chosen to reconstruct all 2-body marginals as well as all 1-body marginals, I can also get the correlated errors between idling qubits. So for example, this one up here, this is a correlated ZZ error between qubits 3 and 4 in the context of applying a C0 gate to qubits 1 and 2. So you can tell that this kind of information is quite detailed, and it really gives you an idea of where the error lays inside of your error budget for this particular cycle. And if you're an experimentalist, and you see a Z error on some qubit while you're actually trying to perform a gate on some other qubits, then you probably think that that's an accidental coherent error. So it's some kind of Stark shift that is unintended. And so what you can try to do is you can try to actually correct this Z error by modifying the definition of your cycle. And so this is a gate-based, so this is not correction at the pulse level, this is correction at the gate level. So what we do is we take, this cycle that we're trying to do, and we say, oh, it looks like it has, 10% of Z error on this qubit. So I'm going to try putting in, a 4-degree rotation on that qubit and see if it gets better or worse. And so that's what we did in these experiments. So these are 2 different experiments. So same experiment on 2 different chips. So what we did is we swept the value of the so I'm aware of time, so I'll try to wrap this up. We swept the value of the error that we swept the value of the Z rotation that we compiled into our gate of interest, and we measured the error rate of that qubit. And so what you would expect in these plots is you would expect that the Z error, which is shown in green, would happen at 0 because not compiling in a Z gate is ideally the right thing to do. But what we found is that this Yorktown chip had such large coherent Z errors on the idling qubits that it actually took like a 50-degree rotation to minimize the error of a Z on that qubit. And so we're showing the idling errors on all 3 qubits as we sweep through these values on each of the 3 qubits. And we did the same experiment for a better device, the Burlington device, but we were still seeing 15-degree angles on this device, or 20 degrees over here. And these kind of plots, there's a very simple signature. So if you have a coherent rotation, it shifts the plot left or right. A coherent Z rotation, it shifts the plot left or right. If you have a stochastic Z error, like a dephasing, it raises the plot up, so you get a higher noise floor. If you have a coherent ZZ interaction, because we're marginalizing here, you actually average over the ZZ, and so it actually looks like 2 instances of dephasing. And if you have, an X or Y error, it can be either coherent or incoherent. You see an oscillation of the X and Y as you sweep through Z. So harkening back to that plot where I showed all of the cycle qualities of all those cycles on all those chips. What's really important to note is that Pauli error is kind of like a coin flip, right? So if you have some error channel S and you apply it to some state, you have a probability that it does nothing to the state, and you have a probability that it takes it to some other state, rho prime. And so if you flip a bunch of coins, and by that I mean you have a bunch of cycles in your circuit, well, what's the probability that you have no error in any of your circuits? Well, it's 1 minus this quantity. It's the sum. It's in the low value approximation. It's the sum of the errors. So you get a very good idea of how well your circuit is going to perform if you know the value of P for each of the cycles in your circuit. So you can put an upper bound on how well your circuit is performing, and you can actually do this rigorously. So you can say, if the ideal output of an entire circuit is rho, and my noisy implementation is rho tilde, then I can upper bound the distance between the noisy and the noiseless versions by epsilon. And everything in this formula is experimentally measurable, because P1 is just the cycle infidelity that we can measure with cycle benchmarking. And so that's what we call quantum capacity, that process that I just explained. So up in the upper left here, just to refresh your memory, this is the plot of all of the different cycle infidelities for all these chips. And so what I've done here is for each chip, I've taken a family of circuits. And I've randomly sampled elements from this family of circuits at different circuit depths. And I've simulated those with randomized compiling. And those are shown as these violin plots. So this is the performance as done by simulation. And then these curves that are plotted over top are just this formula that I've shown here with the values that have been experimentally measured. So what this plot is showing you is that if you have any application circuit on any of these 4 qubits, on any of these 5 devices, and you run it with randomized compiling, this data set will tell you basically how well that circuit is going to perform in practice. And because cycle benchmarking is a scalable protocol, which works just as well for 5 qubits as it does for 80 qubits, you could make the same sorts of plots for there with experimentally measured values of process infidelity. So you might be worried, well, if you're trying to do that, there's so many things to measure. If you have a huge circuit on 70 qubits, that's a lot of measurements. That's a lot of process infidelities to measure. Well, there's the theorem called Ising's theorem, which says that you can edge color any graph which with the maximum degree of the graph or that plus 1. So for example, here I've taken a square lattice of qubits and I've used a famous algorithm to edge color this graph. And so it's possible on these qubits in principle to apply all of these red entangling gates simultaneously. And it's possible to apply all of the pink gates simultaneously. And so there are only 4 different cycles of simultaneous C-naughts which cover the entire graph. And the quantum supremacy paper by Google, they actually had 4 cycles. So they covered their entire graph with A, B, C, and D type cycles. So there's some precedent there. And you can compile any circuit into these 4 cycles if you want, right? So you can take just a single C-naught and you can write it as the product of 2 cycles, which is 2 hard cycles, which consists of simultaneous applications of C-naughts. So basically taking any circuit, you can write it in terms of these 4 cycles, which you can benchmark independently. In practice, you probably want more than 4 because you don't want to have such a dense circuit. So maybe you want to do those 4 and a bunch of specially chosen sparse cycles, and you have a fancy compiler which decides whether to use a dense cycle or a sparse cycle in some application. So there's a lot of room for compiler tricks there. But the point is that the overhead of characterization is not necessarily terrible in a scalable way. Oh, so that's the end. I don't know where my summary slide went. I guess it disappeared. So I'll just go straight to this slide. So thank you for your attention and for this opportunity to talk. I in particular want to say a big thank you to the core scientists and software developers at my company who made every one of these plots possible and took some of the data that I showed on the IBM Q devices. I also want to thank Virginia Frey, who made the RC simulations, and all of Irfan's group for the RC data that I showed. So thanks very much.
Okay, thank you, Ewan, for your talk. Let's clap for our speaker. Okay. So the floor is open now for questions for Ian.
Yeah, you could ask a question.
Please go ahead.
Well, you might have mentioned this in your talk and I might have missed it, or just to double check. So is this agnostic of the error model, the quantum capacity that you're computing?
Yeah, it's agnostic of the error model. So, right. and the reason it is because you're measuring the error model in situ.
So can you use this also to do an error discovery, for example, to understand what's the underlying error model in your system?
Yeah, that's a great question. So the closest thing to that is this plot. This plot, which I talked about pretty quickly, but it's really giving you a breakdown of where your errors are in a given cycle. So say you're doing, a C-naught on these 2 qubits. This column below the cycle is showing you where all of the errors are happening. So in particular, the brightest colors are where you should focus your attention. So in this particular cycle, if you want to fix one thing, it's the Z error on qubit 3. And now you talked about error models. So this doesn't really tell you the error model directly. It tells you which errors are happening in this twirling process.
Yeah, but it seems that you can extrapolate a little bit further and you can actually use it to discover the underlying error model in your device.
Yeah, so if I had a precise error model and it was simulatable, you could do a direct fit to this kind of plot, because in one of the slides, I provided a formula for exactly how to compute these given an error model. So you can compute one of these is for any candidate error model, And then you could do like a minimization to try to minimize your error model with respect to this column plot.
Okay. Thanks.
The twirl aspect of it definitely makes, backing out what the error actually was a little bit confusing, especially if you have strong twirling error, because then, your twirling error is mixed up with your hard gate error.
Thanks.
Okay, other questions for Ian?
I have a question. So how does this picture change when you start to include leakage and non-unital error, right? Because here it's like this model don't take this into account, right?
Yeah, so you caught me. So yeah, this, all of the formalism that I talked about is sort of assuming that there's not much leakage or that you're only measuring bit strings. So I think in principle, everything is extendable to the leakage models if you are reporting the third level. So in that case, you'd actually get a decay on your polydiagonal. And I believe you measure it, but really you should be asking this question to Joel, because he's the protocol expert who can sort of, come up with new protocols on the fly. I guess my short answer is that what I've talked about sort of glosses over leakage, but it's probably kind of okay, but could probably be rigorously extended to include leakage if the work was put in. That's an open area of research.
But I guess, like, do you feel like it's needed? Maybe not.
Well, I mean, I think it's definitely going to be needed at some point. We at least need to bound how much leakage is happening, and whether there's, how much back action is happening, because obviously non-Markovian errors are a huge problem. But as long as you have plots like this, then my answer is I'm not really worried about leakage. And by plots like this, I mean your dominant error is just a simple phase rotation on some idling qubit. And so all of this data was taken with public IBM devices, but I've seen this data for, a lot of systems, including private systems, public systems, and this kind of error is not surprising or unique to IBM systems. So they have very impressive devices, don't get me wrong. I would never want to try to pick on them. I just use their devices because they're convenient to use.
Thank you.
Okay. Any final questions for Ian this afternoon? Okay, if not, let's thank